Let me connect the
radiologist to work
right leg of the
injection.
right arm, left arm, and your right. So now we are acquiring the ECG now. So I am taking the output and monitoring it on the oscilloscope. Relax.
ಮುಂದೆ PQR ಎಷ್ಟು ಬರುತ್ತೆ ನೋಡ್ರಿ. It's coming in form of pulse.
Do the measurement of the heart rate. Just to show the marker on the next QRS. So directly this oscilloscope is giving me the frequency 1.5 Hertz. We convert that into 60, will give his heart rate. 1.5 into 60. 90 beats per minute. So no. Basically, but still probably we can connect it to the low pass filter. It is like you go on building the, adding the blocks and building the system. Every module will have an input and output. Whatever is the output will go as the input to the next module. So that way. So I will switch on the channel 2.
What?
Yeah. Yes, that's what I am doing. So you have ECG without filter with file. Now it becomes easy for us to detect the QRS. So by putting a level detector, we will be able to detect the QRS.
So detect QRS complex
Blue channel 2. So now you will be able to see the cursor. So with every QRS event, you have a pulse which is getting detected. Now we don't want our circuit to detect T wave as a QRS and have another pulse being detected. So to avoid that, what we do is we introduce a refractory period, which is nothing but a monostable multivibrator pulse of pulse width of around 250 millisecond. So around 200 to 250 millisecond, which is a non-retriggerable monostable multivibrator. So within that period, no other pulse will get detected, and we know that by then the T wave would be passed. So let us see the output of this block, and we'll be able to appreciate this.
So only the QRS R wave and this.
So we have a pulse wherein, if you see the pulse width of this, by then the T wave is actually passed. So you don't have any other pulse getting detected, and the other most important part is now I am going to connect it to it. So now whatever we are detecting is the actual QRS after providing the refractory period. Now what we are going to do is convert this frequency into voltage. So we add a frequency to voltage converter block. The detector output. So we sync it with that, basically exactly at the rising edge of the QRS.
So with this input.
Yes. So it has to have a synchronization with the rising edge of the QRS. So that is what we take it as a reference. So now with every ECG being detected, you have a pulse coming out. I am taking it out of a sync pulse here. So 0 and high. So with every pulse that is coming, we get a beep from the buzzer. And we also have blocks like high alarm, low alarm, or a HRV module which we can connect it to a sync output, and then we can even do the HRV analysis or build an alarm setup for tachycardia and bradycardia. So this is just an exploded view of a basic ECG system. The same way you take up any integrated system, we can break it open into a building blocks and understand how this machine is made up of. This is just to give connected to the output of the F2V here. This is in terms of voltage. Now it is around 90, 0.9. 0.9 means it is 90 beats per minute.
Multiplication factor 10.
Yes. So what we have calibrated is, if you get 1 volt, it is 100 bits per minute. Now it is 0.9 volts. So it is around 90 bits per minute. Normally heart rate variability is done over a period of time. It is not done for 10 seconds or 20 seconds. Normally international standard is over 3 minutes or 5 minutes. That is what they take and do the HRV analysis. So we have various amplifier models. So let us look into that.
Minimally same. This is
Oscilloscope is just an output device. I am going to connect just other physiological amplifier modules, and we are going to acquire some biosignals and monitor it. And then we will go to the other stage.
On this unit needs the cell, battery cell.
Yes. So here, if you see here, we have a battery power supply which is nothing but a lead acid rechargeable battery. We also provide a current monitor wherein you can connect a multimeter and see how much each module is drawing. So subsequently, if I add another module, it gets added definitely. So another module, it draws more current.
Get the supply through this
Through this,
cable.
yes. So it not only powers, it also transmits the signals as well. So this cable, if you see here, you have an input, output. Output will be input of the next block. So it's like you are going to cascade it, and then you build a system. That's how it is. These are the elementary building blocks. Normally these kind of blocks were used initially by IIT Kharagpur students, wherein the medical doctors have a course in bioinstrumentation.
What is the cutoff frequency of the low pass filter?
Here we use 50 Hz. 50 Hz. We use a second order low pass butterworth.
Second order.
Suppose if you take by peripheral pulse amplifier, you get the same beats per minute.
Pulse rate will be slightly different from heart rate. Pulse rate we are going to pick it up from the fingers. It is basically a finger plethysmography, what we are going to do. So, I take the peripheral pulse. We have a LED and a LDR. Yeah. So if you see, this is basically a finger plethysmography. Pulse can be obtained from the periphery of the body. It could be fingers, it could be earlobes or toes, at the extreme ends basically. So this is basically a finger plethysmography. So this is not a pulse oximeter. This is a finger plethysmography. Pulse oximeter is different, wherein we are going to obtain the oxygen saturation. Just relax. Now, I will adjust the setting.
Steady state. Steady state.
Ambient temperature.
I'll just connect myself.
ನಾನಲ್ಲಿ ಹೇಳ್ತೀನಿ
Full pulse. You can just do any other signal conditioning just like how we did before. Like just like how we measured the dichrotic notch. That is the dichrotic notch. No, I don't see the normally we have a clip. The clip, then according to the pressure it holds. Now I don't have that right now. It's basically just to already do it. This is the basic peripheral pulse. And contract ಮಾಡಿ relax.
ಇಲ್ಲಿ ಕರೆಂಟ್ ಅಂತ
ಒಂದು ನಿಮಿಷ.
ಕೆಲದೆಲ್ಲ ಇದೆ ಕವರ್ ಮಾಡೋದು ಇದೆ ದಬ್ಬುಡ್ತೀವಿ ಸರ್ ಹೋದ್ರೆ ಹೆಂಗೆ ಸಿದ್ದು
ನೀವು ಫುಲ್
ಬೇರೆ ಇರ್ತೈತೆ
ಬರುತ್ತೆ. ಯು ಆರ್ ಗೆಟಿಂಗ್
ದಪ್ಪ ಇದ್ರೆ ಜಾಸ್ತಿ ಆಗ್ತದೆ ಅಂತ
ರಿಲ್ಯಾಕ್ಸ್.
ಜೋರಾಗಂದ್ರೆ ಸರ್ ಸ್ವಲ್ಪ ಜೋರು
You have to put some effort. Actually, a twitch ಕೂಡ ನೋಡ್ಬೋದು. If you connect these two electrodes, just one fold ಮಾಡಿದ್ರೆ you get that maximum peak spike.
ಅದೇ
That
ಸ್ಪೀಡ್
can-
ಆದಂಗೆ ಅದು ಇದಾಗುತ್ತೆ
So even ಸ್ವಲ್ಪ ಇದು ಮಾಡ್ಕೊಳ್ಳಿ. This you connect it behind the neck.
ಯಾರಾದ್ರೂ ಒಬ್ರು ಇದು ಮಾಡ್ತಾರೆ.
This neck reference. Right side. ಇದನ್ನು right it.
Sorry.
ಹಾಕ್ರಿ ಸರ್ ಹಾಕ್ರಿ ಸರ್
ಇದು
ಆದರೆ ಹೊತ್ಕೋಬೋದು
ಈಗ let's say you should not move your head left or right. Only your eyeball should move. So I'll just make a kind of a small. You focus on this.
ಅಲ್ಲ ಫ್ರೀಕ್ವೆನ್ಸಿ ಕಡಿಮೆ
ಅಷ್ಟು
ಮನೆಗೆ ಹೋಗಿ ವಾಪಸ್ ಹೋಗೋ ಬಂದು ನ್ಯಾಮ್ಕೆ ಸರ್ ನೋಡೋಕೆ ಟ್ರೈ
ಕಣ್ಣಾಗ ಹಿಂಗೆ ನೋಡೋಕೆ ಟ್ರೈ ಮಾಡಿ
ಅಪ್ ಆ್ಯಂಡ್ ಡೌನ್ ಮಾಡೋದು ಆದರೆ ಸ್ವಲ್ಪ
ಮನೆಗೆ ಹೋಗಿ ಹಂಗೆ ಮಾಡಿಬಿಡಿ.
I think he put stress on your. Yeah. ಈಗ
ನೀಟಾಗಿ
ಅಬ್ಸರ್ವ್ ಮಾಡಿ ಡಿಸೈನ್
working with biosignals is very interesting. Basically, yeah, 16 channels, 10, 20. We have different number of channels. Reference. Relax ಮಾಡ್ಕೊಳ್ಳಿ. You have 4 set of prominent frequencies: delta, theta, alpha, beta. So when a person is in an alert state, you have a different frequency which is being occurring. when a person is in a sleeping state or when he is dreaming, when he is in a different state of mind. So already you are getting the EEG. Less than 10 hertz basically. So whatever the frequency that you are getting is less than 10 hertz. So this is not about 10 hertz. So once again this has to be filtered. So between 0 to 3 to 7 or 8, 8 to 12 and 13 and above. So we categorize them into different set of frequencies, delta, theta, alpha, beta.
Any reason between alpha and
So basically,
What at each frequency?
so delta is basically when a person is in a kind of a drowsy state. Theta, once again, when deep sleep. Alpha is once again.
ಅಸೆಂಬ್ಲಿ ಎಲ್ಲ ಹಾಕ್ಬೋದು ಇಲ್ರಿ ಇವನ್ನೆಲ್ಲ ಎಲ್ಲ ಎಮ್ ಎಲ್ ಎಗಳಿಗೆ
What is going on in that? Signal and then channel to the receiver signal. This is the transmitter side and the receiver side. So we can use the same. Noise coming into the picture. Now I will connect this to the modulated output.
And is your power supply includes any EMI filters?
Bring channel 2 down. Channel 2 down. You see now, whatever is being transmitted, I am able to get it from the other side. So this side is totally it is isolated. This side is transmitting, now ECG is in the air, and this side we are picking it up. So this can be even picked up on a mobile phone and then you could do basically this transmission. So wireless transmission. This is using a frequency modulation technique. See, basically when it comes to electrical safety, that is when we talk about all this coupling and things like that. We can achieve different kinds of coupling. It could be an optical coupling also using an optocoupler, or it could be a mechanical coupling using a piezoelectric crystal, or it could be a magnetic coupling using a transformer, or it could be something like a telemetry here. So different methods can be used to achieve this electrical isolation. So if you see this is very safe. I mean, without any thing, the signals are transmitted and this can be sent anywhere. Normally you have various gadgets which are able to capture this, like mobile kind of a devices which can be sent to an Android platform, or it could be sent on any other device to a doctor sitting at home basically. So things, lot of advancements are happening when it comes to the communication part of the communication side of any of these medical devices. Now I have another device here. Basically it starts from 2 megahertz onwards. 2 megahertz we call it also basically used as a fetal doppler. So 2 megahertz and then you go 5 megahertz, 8 megahertz, 10 megahertz, 12 megahertz. This is basically a piezoelectric crystal which is cut into 2 halves. One half is the transmitting side, other half is the receiving side. Now this is generating 2 megahertz and it is throwing 2 megahertz. Now let's say you have an object which is in front of the transmitter. Now this is stationary. So my received frequency is same as the transmitted frequency. 2 megahertz, received frequency is 2 megahertz. Let's say if this is moving away from the transmitter, the received frequency is 2 megahertz minus delta F. If it is moving towards the transmitter, it is 2 megahertz plus delta F. If it is a continuously moving reflecting surface, it is 2 megahertz plus or minus delta F. This delta F is nothing but which is directly proportional to the velocity of the moving reflecting surface. That is what is this delta F, which is what being FM demodulated and then given into a speaker. So we should remember that the ultrasound does not pick up the sound information. It picks up only the movement. It does not pick up the sound. So let us just try to demonstrate that by I'm just dropping a water drop on top of this. So the water drop is moving and then this is sensing movement basically. Now the same thing when I place it over my heart. So it is throwing in the energy and then receiving it. There is no Doppler principle. If you see in ultrasound, the principle is low frequency is primarily used for maximum depth of penetration. 2 megahertz frequency is less, but then it cannot be used for obtaining the information from the periphery of the body. It can obtain information only from regions that are deeper inside. Whereas high frequency cannot have high depth of penetration. They can be used to obtain information from the superficial regions of the body. Just like obtaining the blood flow information, blood flow velocity. You can place it over your jugular or carotid arteries or your veins and obtain the information of the blood flow. I am just giving you an example. Whereas this cannot be used for that. Because 2 megahertz just cannot do that. Whether you have high sensitivity but then there is no much of penetration power. Whether you have less sensitivity, then you have maximum penetration power. So it's kind of inversely related, proportional to that. So we also have a kind of output which can be monitored on an oscilloscope also. I don't have the cable right now, but then this Doppler information can also be viewed on an oscilloscope. Now, just for the fact that we say that this does not pick up the sound information. Otherwise, it should have picked up what I am speaking. Then I can make this pick up what I am speaking by placing it over the vocal cords. Because my vocal cords are vibrating, the same frequency is what being picked up and going here. Just this thing. So it is picking up the movement here, not the sound. Whereas microphone, when we say, that is picking up the sound information. So this is the basic ultrasound Doppler, which we can have it for 2 megahertz, 5 megahertz, 8 megahertz. You can do any studies basically. You have 8 megahertz, you could do even measurement of blood flow velocity. At what angle theta? Theta is what which is going to determine the angle. So you have a particle which is moving and then you throw the ultrasound and then the cos theta is what which is going to determine the response basically. And then that reflected frequency you are going to calculate it using a formula which is readily available. So that can give you the velocity of the blood flow. Now and then this output I give the hospital. ECG is basically a vector quantity. It has both magnitude and direction. So when we are trying to see the ECG from different sides, ECG will appear differently. Basically, it's just like looking into a pen. We see from this side pen looks differently in the side. Whereas I am looking at this, it looks small. So just like that, when we are taking a projection of this, and then you are able to see ECG differently. That is what we are going to see now. So I have connected it to a simulator module instead of connecting it to a subject. Because for me to get this connected, I need to connect a patient cable, wherein all the leads has to be connected. So that is become cumbersome. So we are going to see this now. We have to go it on. So I am straight away getting the lead 1 output. Lead 2 will be normally slightly double of A1 plus 3. So this is lead 3. This is like you can select the leads basically. So this is like your AVR, AVL, AVL. So like this, anybody is interested in studying that particular leads and then doing some kind of research, this kind of system becomes very useful. Whereas the hospital machine, it gives out the complete information, but then you will not be able to record it. So this kind of machines you can directly connect it to a data acquisition. So next we are going to go to the, so far we are seeing only the analog world. Now we are going to go into the digital side and see what we can do. We also have a kind of lot of simulators, like arrhythmia simulator. You need not go and search for data from the hospitals, while you can have a machine which can give you arrhythmias, various arrhythmias. So likewise, we also have a dedicated simulators like pacemaker simulator, defibrillator simulator, wherein this kind of simulations, atrial fibrillation condition, ventricular fibrillation condition. These are some of the arrhythmias basically we call it. Arrhythmia means anything which is abnormal. Which is a machine which is normally used to revive the heart condition by giving an electrical shock or by delivering an energy, very high energy in terms of around 400 joules is what we are talking about. So basically that is done based on whether it is in atrial fibrillation condition or a ventricular fibrillation condition. Because if it is in a atrial fibrillation condition, the energy has to be delivered only in sync with QRS. You cannot fibrillate at any time. It has to be fibrillated only at the onset of QRS. Otherwise, it is like instead of reviving, you are going to kill the patient. It's like that. Whereas in ventricular fibrillation, you just determine by giving delivering the energy at certain amount of energy. If still it is not revived, you increase. So you are going to escalate the energy basically. Nowadays you have this automatic external defibrillators. We call it AEDs. You would have found them in railway stations or in airports or in malls, wherein even a layman can use. Whereas a normal defibrillator, we have to wait for a paramedic person to come and use it. Whereas the AEDs, even a layman can use it, wherein there is a voice prompt which tells what has to be done. Just connect the paddles, don't touch the patient, the machine takes over from there. Even if it detects a faint ECG, it does not deliver the shock. The person could have fainted even just with not being because of heart problem. We don't know whether what could be the problem, whether there is a ECG rhythm coming or not. So when in the event of a sudden cardiac arrest, this AED is coming to help for rescuing. And not only that, we also should know how to do the CPR, cardiopulmonary resuscitation, wherein you do this artificial breathing and also with chest compressions. What happens is, when there is no oxygen supply going to the brain, within a period of 10 minutes, the patient is surely going to die. So that vital period is the 10 minutes wherein you need to do this artificial respiration and CPR, chest compression. Rapid compressions, 30 compressions, and then you do the artificial breathing. Why we are doing it is basically whatever the amount of blood that is there in the heart, it is not pumping. So you are doing it so that in a hope that whatever blood that needs to be pushed to the brain basically. Otherwise, within no time the brain is dead and then the patient just passes away. At least in doing this, you are at least keeping the patient alive till then the paramedics or someone comes and takes over. Or if you have a AED somewhere nearby, immediately that will do this job. So this is something which is of prime importance as far as saving a patient's life is concerned, especially a condition like sudden cardiac arrest. Now we will look into this. This can be imported into MATLAB or LabVIEW or Excel and take it for further analysis. So, what's your name? Right here. If you're come forward. You come this side. Down. So you are able to get the ECG now. So I can vary the speed basically, slow, medium or high based on the time. And then this, you can even place markers just like how you did it on an oscilloscope and do various measurements apart from recording facility. So let us try to record this now. Sampling it at 1 kilohertz or 2 kilohertz basically. So I am sampling it by default here. So I recorded for about 10 seconds. Now this data, let us try to retrieve it in digital values. So from online mode we go to offline mode and then retrieve the saved data. I can just go to insert and do the line joining. This is going to reconstruct and it appears as an ECG. So you have about 20,000 data points because I sampled it at 2 kilohertz for 10 seconds. Around 20,000 data points are available. So this we can directly import it into MATLAB or Excel. Excel is what we are looking at. I don't have a MATLAB here. If you have a MATLAB, you can directly input. So the raw data you need not depend on any other external sources. Directly you can connect to the subject and then read it.
How many channels are the same channel?
This is 10-channel data acquisition system, wherein 10 different physiological signals can be monitored simultaneously. This also does online FFT, offline FFT. So it becomes very useful. For example, like you can put ECG in channel 1 and channel 2 a pulse. You can do a comparison of ECG with pulse or ECG with phonocardiogram, what happens, or ECG with respiration. So like this you can do comparison, or else you can even directly capture 10 different parameters simultaneously. It is like a multi-parameter monitoring system. If you talk about a patient monitoring system in a hospital, normally it will have 3, 4 parameters or 5 parameters at the most. But then there is a limitation, you cannot acquire the digital data from any patient monitoring system. That is unfortunately not available practically. So that was the reason why we thought of having this kind of educational setup wherein you can connect any amplifier. It is not dedicated that channel 1 is for ECG, channel 2 for, it's not like that. Any signal can be connected to any channel and you can do the analysis. So some modules like NI, they have a dedicated facility. This is not a dedicated facility. You can directly connect any physiological signals and you could do the analysis.
So we don't need to do any traditional.
Nothing, directly you can do it and then take it to it's very, very, very simple. Okay, in 2 minutes you can record a data and import it. Everybody should be able to access the oscilloscope. In many institutions we find that not sufficient number of oscilloscopes are available. In some good colleges, yes, but in some colleges only 1 oscilloscope or 2 oscilloscopes. This is something like where everybody can afford, even they can use it and do it at home also. Just connect it to a laptop, it becomes an oscilloscope. So I'll just show this to you.
Cost.
I can vary the sampling rate, I can vary the buffer depth according to my requirement. And I can do even the FFT analysis also. Apart from measuring various voltage parameters and amplitude parameters. It also directly displays when you go to tools. See, when I say measurement, it displays the basic time and voltage parameters. Not only that, you could even do the FFT analysis. For example, I stop it, I go to FFT here. See, I can even expand this and know what is the frequency here, FFT. So this is something which can be achieved. And the beauty is you can do the recording. So you can record it and then export it here. You can record it in JSON or MS3 or CS3. Various formats are available. This can be recorded and just like how we import it, we can import it. This will cost about 10,000 rupees. This DAC. That will cost about 45,000 rupees. With software. We are talking about that is the cost. Very, very low cost. Everyone should afford it and then be able to work on it. In blocks of NI and other things. But then they are very highly priced. We brought it competitively. This will cost about 20,000 rupees, signal conditioning unit. A 2-channel signal conditioning unit with all the basic features of attenuation, gain control, AC coupling, filter on off, selective frequency, offset, excitation voltage, everything. I mean, whatever is.
You can set this parameter.
Yes, all the parameters can be set. And then you can monitor it on an oscilloscope or use this kind of a DAC You can do anything for that matter. It's a generic, once again. You can connect any sensor for that matter. It's a standalone unit at a very low cost. The same NI would run into lakhs, 3 lakhs, 4 lakhs, 5 lakhs. This is something we are talking about 20,000 rupees.